Okay, welcome everybody. Today's lecture is going to be remote, so this is the first of, I think, 2 or 3 videos that I'll be posting for the Labor Day asynchronous lecture. So let's jump right in. For this video, we're going to talk about converting between exponential forms. So there are 2 basically majorly important forms in which we write exponential equations, especially when we're talking about interest and exponential growth and populations and this sort of thing. So the one that we've been talking about so far is we've been writing p naught times a to the power t, where t was measured in years or months or days, and a was the value, which was our ratio by which p naught would increase after 1 unit of time. Okay, so that might have been a year or a day or a month. The other way that we write exponential forms is p naught times e to the power k t. Okay, so these 2 different forms mean the exact same thing. They're simply written slightly differently. So, in fact, we can see here that we could rewrite this second equation as p naught times e to the power k in parentheses to the power t. Because if we have a number to a power and we take that number to another power, we multiply the powers. Okay, so when we look at these first and third forms, it hopefully becomes clear that we're going to see that a is going to be equal to e to the power k. Okay, when we write our equation in the second form, k here is going to be representing our percent interest compounded continuously. Percent interest compounded continuously. Okay, whereas in our original equation, we had a equals 1 plus r, where r was percent interest annually. Okay, so we've got annual versus continuous interest. So let's jump into some of these problems where we're going to be given our exponential form in one form, and we're going to try to rewrite it in the other form. Okay, so the last thing that I want to put in this box is that if we can draw our attention right here to this a equals e to the power k, this is our exponential equation. The corresponding logarithmic equation is, if we apply the natural log to both sides, ln of a equals k. All right, so we're going to be using this blue guy first for problem 8. Then we're going to use our red equation for problem 9 to convert from one way to the other. Okay, so we want to write 7e to the 0.13t as 7 times a to the power t. Well, I know that I can rewrite this as, let me zoom in a little more, 7 times e to the 0.13 to the power t. Now I'm just going to plug e to the power 0.13 into my calculator. I did it beforehand and I got 1.1388 ... meaning there's more numbers as it goes on. I think it's irrational. To the power t. So this right here is our a. We could even go so far as to figure out what r is. Remember, r is a minus 1. So that's going to be 0.1388. okay? That's how we convert in that direction. Let's do another one for practice. I want to rewrite 4e to the negative 0.9t as 4 times a to the power t. So I'll start by keeping my 4, and then I'm going to write e to the negative 0.9 to the power t. Now I know that the inside of this parentheses is going to represent a, so I'm just going to plug it into my calculator, and I get something like 4 times 0.40656 ... to the power t. So in this case, my a was 0.40656. I could even figure out what r is. I would just subtract 1 from that, and I would get negative 0.59343 ... Okay? So, in terms of the kind of verbiage that we use here, k is going to be our percent interest compounded continuously. So for the first equation, let me use a new highlighting color, yellow. This 0.13 here is telling us that we are compounding interest at a rate of 13% compounded continuously. What the bottom part says with our r, this says that equivalently, we can instead compound interest at a rate of 13.88% annually. And these things will be equivalent to one another. Okay, so this is really just terminology. You'll notice that in the first problem, 0.13 and 0.1388 are pretty close. That does have to do with the kind of origins of how this math was invented. But you'll actually see here that in the second problem, when we had negative 90% interest compounded continuously, that corresponded to negative 59% interest compounded annually. Okay, so they're not going to always be super close to each other. Okay, let me clean this up a little bit. All right, now we're going to try problem number 9. I'll leave problem C for you guys to try at home. We'll do the same thing for problem 9. And we're going to try to go the other way. Okay, so like I said before, instead of using the blue equation, we're going to try to use the red equation here. So what I'd really like to write is I'd like to write 7 times 1.2 to the power t as 7 times e to the power k to the power t. And now it's my job to figure out what k is. Well, I know that if e to the power k equals 1.2, then k is equal to ln of 1.2. And that, if I plug it into my calculator, will give me something like 0.18232 ... So if I want to rewrite this, I'll write 7. In here I'm going to put e to the power k, so it's going to be e to the 0.18232 to the power t. Now recall, if I have an exponent to a power exponent, I'm going to multiply those exponents. So I'm going to get 7e to the 0.18232t. Okay. So this was a way of rewriting our original equation. Let's do B, and then I'll leave C for you guys. So in this one, we want to rewrite 0.98 as e to the power k. This means that k should be equal to ln of 0.98. And that is equal to something like negative 0.02 020 dot dot dot. So if I want to rewrite our original equation, we can write P equals 82. P naught stays the same. Inside the parentheses, I'm going to replace 0.98 by its equivalent form as a power of e. So e to the negative 0.02020 dot 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 to the power t. And I want to be really good about the way that I'm writing it. I'll get rid of the parentheses and write e to the negative 0.02020 dot 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 times t. And that is how I convert between these two forms which we use to describe exponential growth and decay.